Welcome to the second of two lessons on assessing the accuracy of remotely sensed data. These are the second introductory lesson, and today we're going to talk about key concepts, okay? So there are a number of key concepts that you want to understand just to get an overview about accuracy assessment. Some of these will apply generally no matter what techniques we're talking about. Some will apply specifically to positional accuracy assessment, some just a thematic accuracy assessment. So the objective here of this lesson is that you want to make sure that you have an awareness of these basic key concepts involved in map accuracy assessment. We won't be able to go into detail on all of these. The goal here is to introduce you to these concepts, but there are 7 more advanced lessons that provide detailed information about each of these key concepts. So this will be an overview. So key concept number 1 needs to be well planned. If you're going to do an accuracy assessment, you need to make sure that you plan it out ahead of time. Okay, the reason for that is that there's really no single strategy. There's no recipe. There's no simple way of doing this. Okay, both positional and thematic accuracy assessment is complex. It's tricky to do. Thematic map accuracy is a little bit more complex than positional, but both are difficult, okay? And if you don't plan it out, you're going to spend a whole lot of money and time that you don't have, okay? There are many issues, there are a number of considerations, and we want to make sure that you have a good understanding of those. There's trade-offs, as I've talked about in the first introductory lesson. There's a trade-off there. You have to balance statistical validity and what you can practically achieve, and that's what all these considerations and key concepts are all about. And then finally, you absolutely must document what you've done so that anybody else who's going to use your map can understand how you did that assessment and then make their own judgment or decision whether what you've done is valid and they can use it or not. And that's critically important. Okay. Key concept number 2 revolves around reference data. You've probably heard the term ground truth be used for reference data. People use it over and over again. I've been on a single person campaign probably my whole career to get rid of this term ground truth, okay? I don't really believe that the ground is always the truth. Depending on how you're doing things, maybe you're actually collecting the reference data from photography or from other digital data or from somebody else, or maybe you even actually go to the field to do it. But even in the field, 2 or 3 people could argue about what the right answer is there, okay? And so I think the term ground truth is a misnomer, and I ask you not to use it. Use something else, reference data, ground data, field data. We assume that the reference data is more accurate than the map that we're assessing, and so I understand why people thought to use the term truth, but it's just not an appropriate term to use. So hope you can help me out with that. We've already talked about this a little bit in lesson number 1, but there are similarities between positional and thematic accuracy, and that's a good thing because once we understand one, we can kind of relate it to the other. So if you start learning positional accuracy assessment, then you learn some of these concepts. You should be able to apply not 100%, but a lot of it to thematic or vice versa, okay? And we know these similarities include some of these initial considerations, like where the sources of error come from and about the classification scheme. Obviously, classification scheme is more important for thematic accuracy, but these days, a lot of positional accuracy assessments are done on LiDAR data or other kinds of data where it's been recognized that the position is highly dependent on the map class. If you're in an open field or you're in a pavement area, it's very easy to identify locations on the ground. If you're in a forest or other vegetation, it might be much more difficult. So classification scheme is important in both positional and thematic accuracy assessment. Okay, reference data collection, obviously, if you're going to do the assessment, you've got to have a sample to compare what's going on your map to what's going on the reference data. And so obviously there's lots and lots of issues. In fact, that's probably the most important thing that we'll talk about through all of my lessons here. Okay, and then once you've got the reference data, then you can actually do the computation of the accuracy measures and then go on and look at whatever analysis that you want to do. So there are some similarities, and that's powerful to have that. Okay. Already mentioned this, sources of error. So you have to pay attention to the sources of error. If you're not well planned, if you haven't thought this out, you yourself can introduce a whole bunch of error into the mapping process. And so it's a good idea to be able to think about that ahead of time. Think about where uncertainty enters into the process or where you think errors are going. And then anytime you can improve that, anytime you can remove those errors that are really not related to assessing the map accuracy, but are due to other factors, then you're going to improve your map accuracy, right? And so that's a really, really good thing. And we could spend hours just talking about sources of error. Okay. Key concept number 5, already mentioned this, is the classification scheme. Okay, it's absolutely key to any mapping project. You have to do it at the beginning of the project. It's critical that you understand what map classes you're trying to map, but also if you have a client, if you're doing this for somebody else, that you and the client agree what those map classes are and how they're defined. Okay, so there are some requirements for an effective classification scheme that you need to be well aware of. One, it needs to meet the user needs. Okay, it can't just be what you think you can do. It has to be what you need or what your client needs. Okay, so that's very, very important. And in order to do that, you want to make sure that you've got 4 criteria that are met. One, that you've got not just the labels of the map classes, but you've got rules or definitions or a dichotomous key or some good way of actually defining that label. Okay. You might think everybody knows what water is, but that's not 100% true, because water could be streams, it could be rivers, it could be lakes. In some cases, it could be swimming pools in the back of people's yards. For wildlife habitat, maybe not so much, but for the local fire department, maybe very, very important. Or everybody knows what a forest is. That's so untrue. There's so many different definitions of the density of the trees and the height of the trees and the crown closure of the trees. Different agencies define those things differently. And so you have to make sure that you've got those definitions. Once you've got the labels and the definitions, then you want to make sure your scheme is what we call mutually exclusive, totally exhaustive, and then a very nice property is for it to be hierarchical. Mutually exclusive means that based on those definitions, you go to a place on the image or a place in the field, and that area can have one and only one label. Okay, there should be no confusion between what's going on. Okay, that's difficult to achieve. You also want to make sure that your scheme is totally exhaustive. In other words, every area on the image gets covered, gets some label. Okay, and if you've done a good job with your classification scheme, that should be true. Now, sometimes there are, some very strange anomalies that go on, and so it's often making sure that your scheme is totally exhaustive to use a category called other or unclassified or something like that. However, if half your map comes out other, then you haven't done a really good job with your classification scheme. Okay. Lastly, we're talking about hierarchical. Hierarchical is different levels of detail. So you start with very general classes and you define them more and more specifically. So for instance, you could start with vegetation, and then you could have woody vegetation versus non-woody vegetation. And then you could take the woody vegetation and turn it into trees versus not trees. Then take the trees into conifer, deciduous, and then take the conifers into pine, non-pine, and break the non-pine down into different categories. Hopefully that makes sense. The interesting thing about that and why it's so useful, especially in accuracy assessment, is you may not have the resources to assess the accuracy of your map at the level 4 classification, because you may have 35 classes at level 4. But if you collapsed upward to level 3, there might only be 18 classes, and you might be able to have the resources to assess the accuracy of those 18 classes. So having a hierarchy is very important. Okay. Lastly, and this is absolutely related to the classification scheme, is something called the minimum mapping unit. If you've done any photo interpretation, you understand the concept of minimum mapping unit. Minimum mapping unit is the smallest area that you're willing to map. Anything smaller than that gets lumped into another category. Anything larger than the minimum mapping unit gets identified as its own area. And that's really, really important. When we get to pixels, people seem to think or eliminate this idea, minimum mapping unit, maybe assuming that a pixel was the minimum mapping unit, but that's a really bad idea. Pixel should never be the minimum mapping unit. There should be some grouping of digital data, grouping of pixels to form the minimum mapping unit. So again, something to think about as part of your classification scheme. Concept number 6, the reference data collection itself. And as I said, the entire accuracy assessment process, whether you're talking about positional or thematic accuracy, depends on this. You need to be very efficient. It needs to be valid. It's a trade-off. You're balancing things here, right? It can get very expensive if you don't plan it ahead of time. So any failure to understand the issues and considerations will doom your entire accuracy assessment, and you have to be really, really careful about that. Okay? So again, more and more details provided in the detailed lessons, but basically when we're talking about reference data collection, the process, we're talking about 3 things: sample size, sample scheme, and spatial autocorrelation. So what are we talking about here? So sample size. Here's the key. The key is that you need enough samples to make sure you've got a valid sample, and you need a good distribution across the map. You can't just collect everything in one small area. Okay, so you need enough, and you need a good distribution. For positional accuracy assessment, the standard NSSDA, the National Standard for Spatial Data Accuracy, says we need 20 samples, but 30 is far better if you can do that. Okay, so 30 or 20 samples per map class. Okay, and when you get to thematic accuracy assessment, it actually is more rigorous. You need 50 samples or so per map class. And you want to avoid this concept called spatial autocorrelation, which we'll define shortly. Okay? Very, very important that you understand that the samples that you take for your accuracy assessment must be independent of any previous data that you used to either register the map to the ground for positional accuracy assessment, or that you used for training data to classify the map using some kind of algorithm or for your photo interpretation. Okay, so you have to have an independent data set, otherwise it's cheating. Okay, and the last thing to recognize here is that if you assess the map of a state, say New Hampshire, then the results are for that state. Okay, and you really can't say anything about individual counties, for instance, within the state. Okay, because you don't have enough samples to talk about that county by itself. So you would need to do another assessment for that county. You can always collapse upward, but you can't collapse downward. Okay, so everybody understands that concept, I think. Okay, sampling scheme. Not going to talk a lot about sampling schemes here, but there are lots of them. Everybody recognizes from a statistical standpoint that randomness is a good quality to have. It gives us a lot of nice statistical properties. But this is one of my favorite slides, because if you're going into the field to collect that reference data, it's not uncommon that you would fall into this kind of situation. Whereas you can see here, you're on one side of the canyon and the random point that you've picked to go sample at is on the other side, and it's going to take you 12 hours to drive around the rim and get to the other side, unless we have a helicopter or a jetpack or something like that. It's not going to work very well. So the sampling scheme is a big deal, and we'll talk more about that in the detailed lessons if you're so inclined. Okay, here's that concept of spatial autocorrelation that I mentioned. Spatial autocorrelation is very important, and you need to understand it when you're doing any kind of sampling that revolves around locational data. Okay, so for remote sensing, that's what we're talking about. So here's a nice definition of spatial autocorrelation. Spatial autocorrelation occurs when the presence, absence, or degree of a certain characteristic affects the presence, absence, or degree of that same characteristic in neighboring units. Okay, so correlation, correlation is a relationship between one thing and another. This is not that. This is autocorrelation. Auto means self, and so this is the relationship of one thing to the same thing, but at some distance apart. Okay, so very, very important, because if you make a mistake in one place, what's the relationship between the errors around that location? Okay, if they're spatially autocorrelated and you make a mistake in one place, then things nearby are more likely to be a mistake as well. It's easy to demonstrate that. Think about, great big cornfield, something that's thousands and thousands of acres. Okay, and you take a sample in, one corner of that field, and you still go a mile away, but you're still in that same cornfield. If you called that cornfield wheat in your classification, then those errors are going to be very spatially autocorrelated. Okay? So when you do sampling, you want to make sure that you have adequate spacing between the samples you use for your reference data so that you minimize spatial autocorrelation. And as I said before, you just can't simply take the samples where it's easy to do so. You have to spread them out, make sure that they're good distribution throughout the map. Okay. All right, on to the statistical analysis that you might do. Okay, so we're going to conduct some kind of statistics based on the reference data and a comparison with the map, whether that's positional or thematic. Okay, and when we're going to do any kind of quantitative assessment, it requires having some kind of statistical result. And for positional accuracy, the basic statistical result is root mean square error, RMSE, and you may have heard of that term before. It's not uncommon in statistics to use. And then for thematic accuracy, the statistical result is called the error matrix, which in statistics is actually called a contingency table or a cross classification. So let's look at that a little bit more. Okay. So here's what we're talking about with positional accuracy. So you can see we've got two data layers here. We've got an image, a digital ortho perhaps, or some kind of high resolution satellite image. And then we've got a road network, and we impose the two on top of each other, and we can see that they don't exactly align. And if you look at the little inset there, you can see that those pink or red circles with the dots in them represent the reference data, and we can see that they don't exactly align with the roads. Okay, and so we're going to calculate the error. How are we going to do that? This happens to be an X and Y, right? The coordinate system. Okay, you can also do this for elevation, but here we're doing horizontal and X and Y, and you would measure the distance from the reference point to the intersection of the road, and you would calculate that in the X direction and the Y direction and record all of those things. And this is exactly what this table shows. Okay, and so you can see we've got the X coordinate for the reference data and the X coordinate for the map, and then we can take the difference of that, and then you can see that what we're actually doing is squaring the difference. Why are we squaring it? Because if you look at the differences by themselves, some are positive and some are negative, and so they would cross out. It's also possible to take the absolute value of the differences, and then they wouldn't cross out, they would add up. But historically and traditionally, it's been that they squared the differences, and so you can see the column that says X diff squared. Okay, and then the exact same thing for Y. We've got the reference data coordinate for the Y coordinate, and we've got it for the map, and then the difference, and then Y difference squared. Okay, and then we take the sum of those differences And then if you look at the bottom, you can see some of the calculations that are done. We can sum all that up. We can take the average. We can calculate the root mean square error, which is the square root of the sum of the differences squared. And from that, we can calculate this standard that we use in the United States called NSSDA, the National Standard for Spatial Data Analysis. Again, this is covered in a lot more detail in advanced lessons if you're interested. But again, remember, we're just introducing these key concepts here for your awareness. Okay. All right. For thematic accuracy, we produce what's called an error matrix. And there's the error matrix right there. And you can see that it's a cross classification. You can see that on one axis is the classified data, or what is actually what the map says, right? Classified not meaning top secret, but classified meaning classified using some algorithm into these land cover categories. Okay, so on one axis we have the classified data. On the other axis, we have the reference data. Okay, and you can see this is a very simple example. We just have three categories: forest, water, and urban. And so if you look, you can see that the map says it's forest 28 times, and the reference data agrees. So where the F and the F coincide, says 28. Okay, so that's the agreement. And then if you look, you can see that the map said there was water 15 times, and the reference data agreed. Okay, and then the map said it was urban 20 times, and the reference data agreed. Okay, so you can see that's called the major diagonal. That's highlighted. Those are the agreements. That's where the map and the reference data agree. But then we have what we call the off-diagonal elements, which are errors of either omission or commission. Okay, it's like a coin. Coin has two sides. Errors have two sides as well. One side is the omission. The other side is the commission. If you omit something from the category it should be in, you're going to commit it. You're going to put it into the wrong category. And so we can see here that once the map called it urban, but it was actually forest. Okay? And once the map called it urban, and it was actually water. Or 5 times the map called it water, and it was actually urban. You see that? So hopefully you're understanding this. It takes a little bit of time to look at an error matrix and figure it out, but once you get used to it, it's really pretty quick. Okay, so what can we do here? So we can take the major diagonal, the ones where we have agreement, and add them all together, right? So 28 plus 15 plus 20 is equal to 63. I have a total of 100 samples. You can see that by adding up the row total or the column total. They both add to 100. And so 63 over 100 is 63%. So the overall accuracy of this map is 63%. And that's fine, but maybe I want to know something about an individual category. Okay? And therefore, this idea of omission and commission comes into this. And this has actually been called in the literature producer's accuracy and user's accuracy. And just for the little quick example, I can show you kind of a little facetiously what we're talking about here. Okay, so let's pretend we're the producer of this map, and we're going to be very proud of our map, and we're going to look at it and we're going to say, okay, look what happened. We're interested in the forest category, and 28 times I called it forest on my map, and it was actually forest on the reference data. Okay, that's the major diagonal value of 28 there. And once I called it water on my map, and it was actually forest. And once I called it urban on my map, and it was actually forest. And so out of the 30 samples that I have in my reference data of forest, I got 28 of those right. So if you go down and look at the producer's accuracy, 28 divided by 30 is equal to 93%. So it looks like I'm doing an excellent job of mapping forest. However, that's only one side of the coin, right? Okay, remember, we've got omission error and commission error. So I've only omitted it twice. So 28 out of 30, 93% looks really good. But you'll see in a minute that I've made lots of commission error to make sure that I got all my forest. Okay, so now let's pretend I'm going to be a user of this map. And so you and I are going to go out and have a picnic lunch. And of course, we want to have the picnic lunch in the woods, right? In a nice spot in the woods. So what happens? So on my map, again, I've called 28 areas forest, and they were actually forest according to the reference data. So I'm happy about that. But I've also called 14 areas forest that were actually, according to the reference data, water. And I've called 15 areas forest when, according to the reference data, they were urban. And so I've actually labeled 57 areas on my map as forest, according to this error matrix. You can see I've made a lot of commission error. I've called a lot of things forest that weren't forest. And so if I go down to the user's accuracy at the bottom there, you can see that I got it right 28 times, but I called 57 things forest, or 49% of the time, something that I called forest was actually forest. In other words, if we use this map to go have a lunch in the picnic in the woods, okay, we're going to end up with a better chance of drowning or getting hit by a car than we are ending up in the woods. Okay, does that make sense? I hope that it does. You need to look at this a little bit, kind of stare at it. There's lots of examples in the literature where you can look at this and understand better. It just takes a little bit of time, but I'm sure you'll get it. Here's another example. You can see there's an accuracy assessment site. The map labeled it as water, and the reference, yes, it was water. Site number 2, pavement. The map called it pavement, but when we got there, it was actually rooftop. Site number 3, pavement, and actually the reference label called it pavement. And site number 4 there, vegetation, reference label called it vegetation. And so step by step, you can go through and then use this information where you've got one column of what the map said and another column what the reference said, and use this to fill in an error matrix. So hopefully that helps clarify the process of building the error matrix a little bit more. So a little bit of a summary of what we learned in the lesson today. So if you're going to spend the effort to conduct an accuracy assessment, do it right, okay? Spend the time, plan it out, think about it ahead of time, consider all the things that you need to, take the time that you need to go through the process before you begin so that you're in really good shape and you get a valid and effective accuracy assessment. Remember what we're doing, right? We're balancing statistical validity with practical application, so that's really important. And don't forget, you've got to document your process so that you show your results. Okay? We need to know how you did that so we can judge what's going on. So I hope you've enjoyed these 2 introductory lessons. I appreciate your attention. Thanks.